Welcome, class. Here we are, lecture 10, moving right through the course. So we've now gotten to a position where we've identified different statistical ensembles, characterizations of the statistics of microscopic fluctuations under different physical constraints like constant energy or constant temperature. And we've introduced the partition function, the sum over all of the states weighted by the appropriate likelihood of observing some state. So this partition function is a normalization of that probability distribution. And we've demonstrated that it contains a ton of information. It really just boils down to computing that partition function in cases we care about and getting some insight into strategies for evaluating that sum and ways of representing the system. So we've started a discussion a little bit on, when will classical representations, assuming particles behave like classical objects, is reasonable, and when we have to confront quantum mechanical details. So we're going to continue essentially right where we left off last lecture by exploring another explicit calculation. Last lecture, we evaluated the partition functions for free particles moving around in boxes, both quantum mechanically and classically. Today, we'll include a little more complexity in that the particles will no longer undergo free motion, but will be confined to some harmonic potential. So we'll consider classical and quantum harmonic oscillator models and compute their partition functions, understand the implications of those partition functions, and learn a little bit about physical realizations of harmonic oscillators like dimers in solids that you actually see out in nature. Okay, but to begin, let's remind ourselves of why this partition function is so useful. So for example, the so-called canonical partition function denoted Q is evaluated for a system with fixed temperature, volume, and number of particles. It is defined as a sum over all possible microstates of the system, consistent with a fixed volume and number of particles. And that sum is over Boltzmann factors, e to the minus beta, the energy of that microstate. And we know that, for example, if we were able to evaluate capital Q, that would tell us directly about the Helmholtz free energy of the system under those conditions. Similarly, if we could evaluate Q and know its functional dependence on beta, so be able to evaluate this derivative, we would know the average energy of the system. If we could evaluate two derivatives, we would get a sense of the scale of fluctuations of that energy, and thus have access to the heat capacity of the system. All right. So those are all properties embedded in the partition function. We just need to develop strategies to compute it. And one of the strategies we introduced last time was how to consider systems which were non-interacting. So a non-interacting system is one in which the energy can be written out as a sum of the energy of particle 1 plus that of particle 2 particle 3, all the way up to particle n. That linearity, that independence of particle 1's energy on any other particles implies that the statistics of the entire microstate, all the numbers that describe the state of particle 1, particle 2, particle 3, well, when the energies are decomposable, when they're independent, the statistics are analogously independent. It factorizes into a probability of observing the particle 1 in some microstate times the probability of finding particle 2 in some microstate, all the way up to particle n. Now, an interacting system would be one in which the energy depends on both where particle 1 and where particle 2 are with respect to each other. For example, if I had a pair potential through which they interacted, and thus, as a consequence, the probabilities would depend on two particles at once, and thus would not factorize in the simple way that we see here. Nevertheless, for non-interacting systems, this is always the case, and it follows from this factorization that the partition function will similarly factorize into n products of a partition function for the individual particle. Which we have denoted a little q and called that little q the single particle partition function. So it is all of the thermally accessible states that a single particle can occupy. And in instances when the system is not interacting, knowing it, and if all the particles are the same, we thus have access then to the total partition function, which is just n factors of, of that little q. Assuming all particles are the same. So that takes what would be a really difficult calculation, summing over all of the possible states by summing over all the possible ways that particle 1, 2, 3, all the way to n are at one time, moving one of them, resumming, etc. If we can evaluate just all the states that particle 1 can be in, we know all of the states that all of the particles can be in. Okay, and we evaluated this explicitly for a system which could only translate so when the energy was just kinetic energy, like so, and evaluating that, say, in one dimension, following classical mechanics, we found that if the particle was confined to a box of length L, and we counted up space in chunks of delta x and delta v, that those kinetic energy states, when summed over, gave us a factor of 2 pi over beta m to the 1/2. And we found that if we did that same calculation quantum mechanically, again, one dimension, denote quantum mechanically with a qm, the mechanics by which we did that sum were different. We had to know what the energy eigenvalues of the particle in a box are and how you represent its energy. Nevertheless, one could figure that out and summing over them in an appropriate limit, appropriate for a particle in a macroscopic box, we found the partition function now to be something that looked very similar to what we got classically, with the important distinction that we didn't have to introduce a resolution, an artificial resolution with which to count space in X and Vx into. So quantum mechanics essentially provided that scale for us explicitly in terms of the discrete eigenstates that a particle can exist in. And by imagining that these, by asserting that these two really are equivalent, we essentially work out a reasonable way to set the scale by which we can compute states, and that's given by Heisenberg's uncertainty principle. And we noted that both partition functions had a simple functional dependence on beta, implying an average energy which was the same and equal to 1/2 kVt. So pulling those lessons together, we note that for a particle undergoing pure translational motion, we can evaluate its partition function. If it's independent, we solve for little q and essentially learn that for consistency, quantum mechanically and classically, we can decide to count space up, phase space, this delta x, delta v, up in a specific way. And if we do that, then we'll get consistent answers. Generalizing that translational motion classically, we found another important lesson, which is that classically, even for an interacting system, even in an arbitrarily complicated potential, the spatial degrees of freedom, denoted here by Rn, where all the particles might be in space, and the momentum degrees of freedom, p to the n, we found that it is always the case that they are statistically independent. That results from the fact that the energy classically is decomposable into a sum of a potential energy piece and a kinetic energy piece. The potential, depending on the spatial positions, the kinetic depending only on the momentum degrees of freedom, and then that linearity again implies statistical independence or a factorization of the partition function. So for a classical system, generically we'll have a piece due to the kinetic energy, something we can always evaluate because the kinetic energy is always a sum over single particle kinetic energies. And in general, some piece due to the potential that we called last time the configurational piece. So this is the potential energy. That's the kinetic energy. That linearity, that summation of those two pieces, classically, where those are really just numbers, they aren't operators. So when I put them up in the exponential, I can write the exponential as a product. Thus, I can separate out all of the microscopic counting, all of the partition function calculation into a part which we can always do, kinetic energy part, and a part that might be difficult, the potential energy part. Note, if those two are operators, if I put them up in the exponential, I can't separate that exponential into a product anymore. That would assume that those operators commute, which in general they don't. So generally, quantum mechanically, position and momentum are correlated. So we can flesh this out by reminding ourselves of an explicit calculation we did last week before we carry on to generalizing this for, or maybe working through a more specific example in the case of harmonic oscillators. If we consider n particles interacting with some arbitrary potential, and let's, for simplicity, imagine that they all have the same mass. It just simplifies our notation, doesn't make anything conceptually distinct. Then the total energy is a sum of where particle, a potential piece that knows and depends on where particle 1 is, where particle 2 is, all the way up to where particle n is. A kinetic energy piece, which we can always write down as a sum over 1/2 m modulus of the ith particle's velocity. That's kinetic energy. Let's actually write that in this case as momentum to be consistent with the notation up here. So if a classical system interacting arbitrarily has that decomposition of its energy, then the partition function, which if we use the resolution suggested by quantum mechanics, will give us a factor of h to the 3n, because I have 3n integrals to do, some of which are positional ones, like integrating over all the places R1 can be, R2 could be, up to Rn. Those are weighted by this potentially complicated potential energy term, but nevertheless, all of that exists separately from the integrals over P1, P2, Pn, the momentum integrals, each of which are weighted by their own factor of 1/2. So if that's momentum, that m goes downstairs. Right? This is just a slightly different representation of what we've seen before when we wrote things down in terms of the velocities. Now, each one of these factors in the Boltzmann factor for the kinetic energy can get distributed to its own integral. Each one of those integrals then is a Gaussian integral, which means that we can do them, and when we do them, we'd get the typical Gaussian result of 2 pi playing the role of a here. I get a factor of m and a beta underneath. And that would be under a square root. But now I need to count how many integrals I've done. So these are vectors, so there's 3 of them in each one of those integrals I've written. And then there's n momentum, or n particles to integrate over. So altogether, I have 3n factors of that Gaussian integral. So the partition function has a piece due to those momentum degrees of freedom that we've just computed, and that resolution as suggested by quantum mechanics. And that'll give us 3n factors of this 2 pi m over beta h squared. And we can call that leftover integral over space QC, that configurational integral, which may be very difficult to evaluate. If the potential is 0, what does that integral end up looking like? So if the potential is 0, I'm just integrating 1 over the domains of all of those integrals. One factor will give me, say of R1, will give me all the places I can put a particle 1, in some volume, which is then just V. And I have n factors, so I would have V to the n. Now, it's likely that if all those particles have the same mass, they are therefore statistically indistinguishable. So I'll need to account for that indistinguishability by a permutation factor n factorial. And then there's a really concise way to represent this if we note that this is essentially a unit of length. That means that we have some QC over n factorial measured in 3n units of length. This lambda, the thermal wavelength. Equal to h, Planck's constant, over 2 pi m kBt square root of. And indeed, you can see that that indeed must have units. Q is dimensionless. It just counts the number of microstates. If QC in the limit that Q, or in the limit that U is 0, is just a volume to the n, then I need units to cancel out those units of volume, and those are given to us by the thermal wavelength. So it's essentially, that is essentially an effective resolution by which we count particle positions, and that knows both about Heisenberg's uncertainty principle, so a lower limit beyond which it doesn't make sense to identify a unique microstate, and is smeared out by the fact that particles' velocities essentially enter in here through setting that length scale. So there is a thermal uncertainty, a thermal length scale over which positions are unique. There's a length scale over which there's a meaningful distinction between one spatial microstate and the next. From that partition function, we can always compute the average energy by then taking the appropriate derivative. The fact that we have a product entering into the partition function, when we take the log, becomes a sum. So I can then take the derivatives of that sum independently. This would localize, the first derivative localizes the potential energy on average, and the second piece is just taking the derivative with respect to beta of this factor here, whose beta dependence is beta to the minus 3n by 2. The minus sign out in front of that derivative cancels that minus sign, and I'm left with 3n over 2 factors of 1 over beta, which is kBt. So essentially 1 factor of 1/2 kBt for each of the 3n momenta that the particles have. This factorization of the partition function implies a factorization of the probability. So the probability of observing some the factorization of the probability of observing a specific value of the energy, this means that the probability of some potential energy fluctuation is statistically uncorrelated with a kinetic energy fluctuation. So really, it is a very strict statement that the potential energy changes through particles changing their positions, their spatial arrangements. Even if they interact with a very complicated potential, those fluctuations happen completely independently of how fast those particles change those positions in. Just as a little aside, we've discussed quite a bit this notion of statistical independence from the factorization of a probability. We can note that more generally, if I have some joint probability of two fluctuating observables, say A and B, this could be the probability that I flip a coin and get a head and roll a die and get a 2, for example. If those two objects, those two outcomes are statistically independent, that joint probability, the probability of getting one outcome and simultaneously the other outcome, factorizes into just the product of the probability of that first outcome times the second outcome. Oops, sorry. If A and B are independent. Which also means that the average of A times B, because if the statistics of A are independent of the statistics of B, I can average A separately from B. So statistical independence implies that fluctuations and also averages can be considered distinctly or separately. Okay, so that's a kind of overview of what we've learned classically. So even for a complicated interacting system, we've gotten this simple result that the kinetic energy fluctuations can always be done independently. So for all intents and purposes, we never have to worry about the calculation of the kinetic energy or its contributions to statistical properties. We know it's always going to be that simple answer. Okay, so now let's think a little more concretely, a little more specifically, and consider another exactly solvable system that we can learn some lessons from. And this leads us to a discussion of the harmonic oscillator. And let's start by considering it in one dimension. So the energy function for a harmonic oscillator, well, it's got kinetic energy like we had before. Let's write that in terms of momentum. So 1/2m, say some x momentum squared, that's the kinetic energy. But now in addition to having kinetic energy, it has potential energy. And let's write this in a specific way. 1/2 depends on the position of the particle in some harmonic potential, x. And let's denote the spring constant as m omega squared. Omega being the frequency of the oscillations of that particle in that harmonic well. Okay, so that's the energy function. If we're going to compute the partition function, we need to identify microstates, which again brings us to this point of whether or not we should consider this problem quantum in the quantum context or in a classical context. We'll do both. Let's start classically. So classically, the microstate is completely defined by two numbers, where the particle is and where it's going, position and momentum. I can thus compute the single particle partition function by summing over all the places it can be times all the momentum it can have. I need to count those with some resolution, and let's get it with resolution of an arbitrary box size delta x and an arbitrary momentum size delta p. And now I have my energy, my Boltzmann factor, 1/2 m omega squared x squared. There's the potential energy piece, and beta times 1/2 over m px squared. Now, that exponential of a sum is a product of exponentials. Like so. That's true classically, where those x's and p's are numbers, not operators. And this one, I can pull through the momentum integral. It's independent of momentum. I can put it under that x integral. Oops. And thus I can do those integrals independently. And now I have to ask, well, what should my limits of integration be so I can evaluate those integrals? So momentum in principle can be anything from -infinity to infinity. Now what about x? Before, when we thought about confining a particle to a box, this is a canonical partition function calculation, so that box needed to be held fixed such that the volume was fixed. That would suggest that dx needs to be integrated over some finite number. However, if the spring constant is effectively strong, such that the particle is well localized to some region of space that keeps it from sensing the volume of the box, as was done in the calculations of Stirling's approximation, I can essentially set these limits to be -infinity to infinity and not worry about the domain of that integral that doesn't actually fit into my volume, because that will contribute a negligible amount. Okay, so then I have two Gaussian integrals. I know how to do those. That's great. I'll get 1 over delta x times, now playing the role of a in our Gaussian integral is a beta m omega squared, and I'll have that under 2 pi. The momentum integral gives me analogously a 2 pi, an m, and a beta. Right. Now, if we look at that, it's functional dependence on beta, where I have two factors of beta to the -1/2, so that whole thing is proportional to beta to the -1. And should I take the derivative of log of q with respect to minus beta, I would have generated the average energy, and I can do that, and I would find that I get 1 kBT. Now note, in this case, I had two Gaussian integrals, two quadratic variables. And the result is twice 1/2 kBT for the average energy. So this is something that manifests what we saw previously when we had 3 n factors of a quadratic variable in a set of particles and a set of n particles in a 3-dimensional box. We got 3n times 1/2 kBT contribution to the average energy. In fact, this little bit of arithmetic has a fancy name. You call the fact that anytime you have a quadratic variable in a classical system, and the fact that it contributes 1/2 kBt to the average energy, you call that the equipartition theorem. It's a very highfalutin name for the consequence of a Gaussian integral. Stated in words, one would say that any independent classical Gaussian degree of freedom, so entering in the exponential quadratically, each one of those will always contribute identically 1/2 kBt to the average energy. So should one give you a energy function that's a set of quadratic variables that are independent, the system can be treated classically, so you could factorize that exponential. You could go through the partition function calculation, doing those Gaussian integrals, and then take the derivative of the results with respect to beta. But what you would find is that each one of those will just always contribute that same amount of 1/2 kBt to the average energy. Note that that contribution is independent of whatever spring constant it was, just like the contribution in the kinetic energy is independent of the mass of the particle. Okay, so that is the classical results. So Q is all this business. Let's now proceed quantum mechanically and see what we find. All right, quantum mechanically, we have to think about energy levels. So if that's my potential, I know the energy levels for a harmonic oscillator look something like that. Well, this is some N0 state, this is some N1 state, and each one of those energy levels is separated by the same amount, h bar omega. So I can determine the state of my system by just knowing what eigenstate it's in, what quantum number it's in, and this is something which will run from 0 to infinity. And I know how to assign an energy to that state. It's h bar omega n plus 1/2. So I have everything I need in order to evaluate the partition function. I have a representation for what to sum over and what goes in the argument of the exponential. Okay, so Q then is a sum over n from 0 to infinity, e to the beta h bar omega n plus 1/2. Now I'm going to write this down in a slightly specific way. I can pull out that factor of e to the minus beta h bar omega by 2. That's a constant independent of the integer n, the index I'm summing over. And what I'm left with after I pull that constant factor out is e to the minus beta h bar omega times n, but I can write times in a fancy way as raising that exponential to the n. Now note, a sum from 0 to infinity of some number, it's a complicated looking number, but it's just some number, to the n. This is a well-known sum that can be evaluated. It's a geometric series. So that sum is evaluatable. I can do it. I have this constant factor I've pulled out, and a geometric series gives me 1 over 1 minus the number that's being raised to the n. In this case, e to the minus beta h bar omega. If I multiply top and bottom by e to the h bar omega, beta h bar omega, I would recognize that that is nothing but twice the hyperbolic sine function of beta h bar omega over 2 inverted. Nice compact way to represent that. Okay, well, that doesn't look very much like the classical result we got. But remember, to get the classical results in the translational motion calculation, we did something kind of fast and loose. We approximated a discrete sum that we couldn't do as an integral, which was valid in a high temperature limit where that Boltzmann factor varied slowly. The energy spacings were very small relative to kBt. So what happens here if we take that high temperature limit? Will we get something that looks like the classical result again? All right, well, what's the high T limit? So high T is the same thing as beta going to 0. When beta goes to 0, the factor e to the beta h bar omega over 2 could be Taylor expanded to 1 minus beta h bar omega over 2. So I could Taylor expand that numerator like that. If I Taylor expand the denominator analogously, I will find that to leading order, quantum mechanically, I have 1 over beta h bar omega. That's just what it is, just a number. The energy scale h bar omega in units of kBt. Now, classically, what did I get? So if I pull this result up here, that's the full result, but I can simplify things. So I've got a factor of m here and m here. I've got a factor of omega squared under the square root. So I could pull that out, and I've got 2 factors of 2 pi. So I'd get 2 pi, 2 factors of beta, square root of gives me 1 factor of beta. And then I have an omega, and I have delta x and delta p. Now look at that. Again, if we take this artificial resolution, delta x, delta p, to be equal to h, both estimates will agree. 2 pi h over 2 pi is h bar. So that's nice. We have consistency again and again only when we expect to, only when the discreteness of the energy levels are not important in a temperature, when we're working at a temperature high enough that those energy levels blur together. What about the low temperature limit? A way of thinking about that is when beta goes to infinity. When beta goes to infinity, e to the minus beta h bar omega is much, much less than 1. So Q would be approximated as e to the minus beta h bar omega, the first term of which, so this denominator here I can ignore. So 1 over 1 minus a really small number to 0th order is just 1. To first order is 1 plus that small number. So if I took that, the next term would be e to the minus beta h bar omega times 3/2. The next term would have been e to the minus beta h bar omega 5/2, and so on. So indeed, I pick out only the lowest order pieces of that sum. And in the high beta, low temperature limit, each term is smaller than the rest. So the leading order, we could just take the 2, h bar omega, like so. So at lowest order, when t goes really small, essentially it's just like I have a 2-level system again. If I imagine energy, I have some ground state energy, which is h bar omega. Let's not say that. Let's just set that ground state energy to be 0. We have some first excited state. That's a delta epsilon away. And that delta epsilon we've just found is a factor of, sorry, this must be a factor of 1/2. There you go. So that delta is just h bar omega, one factor of h bar omega. So a 2-level system, which is exactly given by just these 2 energy levels with some delta epsilon between them, its partition function you evaluated in your homework is just 1 plus e to the minus beta delta epsilon. That has an average energy, which is really easy to compute. It's just delta epsilon times 1 over 1 plus e to the beta delta epsilon. So the 0 of energy is just 0, and then 1 over 1 plus beta delta epsilon is just the probability of that excited state that has a corresponding energy of delta epsilon. That goes to 0 as t goes to 0 or beta goes to infinity. So indeed, a 2-level system crashes down into its ground state as the temperature is lowered. It's useful to cast this harmonic oscillator at low temperatures as this effective two-level system because its fluctuations in energy are really easy to evaluate for that two-level system. The derivative of log with respect to beta twice will give me that. Or the second derivative, or the first derivative of this average energy, that gives me a factor of epsilon delta squared, e to the beta delta epsilon from the numerator, and then 1 plus e to the beta delta epsilon, now squared in the denominator. If beta is really, really large, that denominator, the exponential part of that denominator is going to overwhelm the 1, and I will arrive at the fluctuations in the energy is just that gap squared times a factor of e to the minus beta delta epsilon. I get the two factors from downstairs. When I say that that's much bigger than 1, it cancels 1 from upstairs, leaving me with a minus in the argument altogether. So an effective two-level system has a very simple way to think about its energy fluctuations. It's just this scale. There's a scale, delta epsilon, by which the energy can fluctuate, and then I have some probability that that fluctuation has happened, manifested here in this Boltzmann factor, e to the minus beta delta epsilon. Graphically, we can make a plot of average energy as a function of kBt. Then for our harmonic oscillator system, playing the role of delta epsilon is this h bar omega. Our harmonic oscillator has a non-zero ground state energy of h bar omega over 2. Now the classical results said that the average energy was just kBt, so that's a line two factors of 1/2 kBt. That's the classical equipartition result. Quantum mechanically, we know we start in the ground states. We will approach that classical result. And the relevant scale by which we begin behaving classically is when kBt is going to be much, much larger than that relevant energy scale set here by h bar omega. So we see strong deviations from the classical result at temperatures lower than the characteristic energy scale for excitations. We can plot the corresponding heat capacity as a function of kBt. Where again, behooves us to denote this relative to that energy gap. Now, the classical results, if the classical result, that's a terrible classical result, that's hard to read. Again, looks like an H. The classical result, CV, is just the first derivative of the energy with respect to temperature. The classical result is a line with constant slope. The classical heat capacity, therefore, is just a constant. It would be a constant at KB. The quantum mechanical result, we know, will approach that and do so exponentially as we learned in this effective two-level system. At really low temperature, the system is down only in its ground state. It does not fluctuate. So at low temperature, there are no energy fluctuations, and correspondingly, the heat capacity is 0. So this should be a little flatter. And then there's some interpolation that will look something like that. Again, meaningful fluctuations start happening when the temperature is on the order of that h bar omega. So that's the QM result. So what we learned by making these plots and doing this analysis is that for the harmonic oscillator, quantum mechanics really matters when kBt is much, much less than whatever characteristic energy gap fluctuations face. All right. So that's the treatment of the harmonic oscillator. It behooves us to think a little bit about when that harmonic oscillator is a reasonable model for a realistic material. So when is it? Where do we find harmonic oscillators out in nature? Well, one case is that of intramolecular vibrations. So imagine I have some diatomic, some heterodimer. It's got some bond length, let's call that little r. And if I were to plot the potential observed for stretching that bond, asymptotically the bond can break. Pauli exclusion says that it's going to be hard to overlap those particles. So a typical bond dissociation curve might look something like this, having some minimum energy and some typical bond distance. Now that is not very harmonic, but locally it is. So if I look at fluctuations that are small relative to that see excursions only small distances away from that minimum energy configuration, it is probably a reasonable approximation to say that that potential is locally harmonic. That is to say that I can take that full bond dissociation curve, and for small displacements, I can Taylor expand it as a constant u min. It's symmetric, so the first order derivative goes to 0. I have then a second order derivative with some characteristic mass of that mode and frequency of oscillation. That grows with displacement away from that minimum energy. Now, intramolecular vibrations are typically very stiff. Such that omega is very large, and correspondingly delta E is much, much greater than kBt. So for example, if we thought about, say, an OH stretch, the vibrational frequency, does anyone know? It's about 3,000 wave numbers. This is a terrible energy unit, but if you put kBt in those units of energy, it's about 210 at 300. So indeed, typical vibrational excitations are very large on the scale of thermal fluctuations. So most covalent bonds, their vibrations at ambient temperature are in their ground states. You see very fleeting, very few excited vibrational states just over the course of thermal fluctuations. That's why we take powerful lasers to put enough energy into those molecules to explore vibrational dynamics, because otherwise they're just sitting at their lowest configuration. Now, that's not to say that there aren't very low frequency vibrations in complicated molecules. Those exist too. So this is a statement of typical covalent bonds. Okay. So there's not really interesting fluctuations in molecular vibrations caused by thermal energies. But another case that harmonic oscillators come up in, as we have alluded to a little bit in discussion, is at low temperature in solids. So imagine I have some crystal, for example, which is some ordered arrangement of particles, maybe something like this in 2 dimensions that repeats. So I could think about labeling those particle positions with some vector r. This is some crystal. So I could think about low temperature fluctuations of a crystal. I could also think about low temperature fluctuations of a glass, so an amorphous solid. Again, that is an infinite system. Either of those two at very low temperature don't experience large fluctuations in their particle positions. And so if R doesn't vary much, I can imagine defining some typical value of that position, call it R0, and then asking for small fluctuations about that R0, which we can assume are small. And let's let this be the equilibrium or zero of energy position. All right, so if the positions of particles don't move very much, I can imagine asking for how the potential changes due to those small fluctuations in the position. There will be some 0th order term where all of the particles are at that energy minimum. First order terms, if the solid is stable, means that there's no first order derivative, but there is second order derivatives. And they're complicated because I can ask the derivative as I make small changes in the ith particle position or the jth particle position. And there's a matrix of partial derivatives with respect to the ij movements that I will call K. And that matrix is probably complicated because it tells you about how the total potential energy changes as they make small changes to the ith and jth particles position. But we know that whatever this K is, it's symmetric. And so if it is symmetric, it could be diagonalized. If it's diagonalized, we would have a set of eigenfunctions and eigenvalues. The eigenfunctions we call a set of modes. Which are going to be writable as linear combinations of the delta R's. And let's call those linear combinations C alpha, alpha for the alpha normal mode. Written in terms of those normal modes, the energy, the total energy, potential, and kinetic has a simple structure. They're all independent, so I can sum the energy from 1 to 3n. The kinetic energy associated with that mode, which is its time derivative squared, some mass of that mode, and some harmonic potential acting on that mode, like so. And so when I do this diagonalization, I find these eigenfunctions that uncouple all of those small displacements from each other. I have an energy writable as a sum of independent contributions, which then is a non-interacting system that I could solve exactly. So the average E, for example, is just going to be how many quadratic variables I have, in this case 3n, times 2 for a quadratic variable associated with the potential and with the kinetic energy. And then each of those through equipartition contributes kBt worth of energy. That would be the classical result. And if I wanted the heat capacity, I just ask her how does that average energy change with temperature. And in this case, it would just be 3n times kb, which is a fancy result in and of itself. That's the result observed first by Dulong and Pettit, and now named the Dulong-Pettit law for the heat capacity of solids. There's a little bit of interesting history about these sorts of observations of the heat capacities of solids. If you actually go in and measure it as a function of temperature, indeed you find that at relatively high temperature, this Dulong-Pettit law holds. So experimental data do collapse at high temperature to some simple integer number of kBs. However, if you measure this at low temperature, there is significant deviations. So looks something like that. So there are experimental data one could go look up. Would look like so. And if you actually ask for how does this heat capacity rise at really low temperatures, it turns out to rise in proportion to T cubed. And that's a bit of a puzzle, actually. Why would it go like T cubed? At low T, we know quantum mechanics is why we have this deviation from the classical results. But at low T, as we've discussed, we have essentially two-level system. The CV per kb we worked out for a two-level system is beta epsilon quantity squared, so whatever the gap of that two-level system is, times this Boltzmann factor. But in a solid, you know, those gaps are related to the frequencies, and in the solids, this normal mode representation we've just written down says that there are lots of different frequencies. Each alpha mode has a different corresponding frequency. So for the whole solid, which is what's being measured, the total heat capacity is going to be a sum over all of those modes. Or if those modes are continuous, we're going to approximate that as an integral. So we're going to integrate over all of the different alpha modes times each's contribution to the heat capacity. So the gap is h bar omega. And now this factor here, G, we've introduced is the number of modes with some frequency between omega and omega plus some d omega. So it's a density of modes. How many modes are there with a specific frequency? So essentially, to understand why there would be a specific functional form to the heat capacity at low enough temperature, we have a simplification which says that the system will act like a set of two-level systems. But to understand that temperature dependence, we need to have a model for how many modes there are at a given frequency. So what this density of modes, density of states, G of omega is. All right, so this is a fun little game, and in fact, resulted in a fun little argument between two very important people in the history of statistical mechanics. This gets us into a little bit of a history lesson and a fight that Einstein and Debye had. So Einstein, really the first to consider this problem, asserted his picture of vibrations in a solid was essentially that he could imagine tagging a particle in this periodic arrangement. And that particle would undergo small displacements around its equilibrium position, essentially localized fluctuations in this solid. And so he assumed that every particle vibrated in some cage. And it did that with some characteristic frequency, call it omega knots. And so G of omega was nothing but how many omega knots there were. So 3n if there are 3n particles, or if there are n particles in 3 dimensions, each one of them having that exact same frequency. So this delta, this is a Dirac delta function. Which gives us a simple solution for the heat capacity. So that's an integral we can do, and we'll get CV per KB is just then 3n times beta h bar omega knots squared times this factor of e to the minus beta h bar omega knots. But if you look at the temperature dependence there, the temperature dependence vanishes much more quickly than T cubed. In fact, leading order goes like 1 over T squared dressed by an exponential, much too quickly, much more quickly than the T cubed results observed experimentally. Now that result, to all fairness to Einstein, clever guy, the experimental result didn't exist when he made this prediction. He was pretty bold in that way. He just worked out quantum mechanics and thought about photons and then applied the same sorts of mechanics to this question of phonons, those lattice vibrations. And later on, when the experiment was done, showed that this model was not quite right. In comes Debye, who proposed a different model. He said that vibrations are not independent, that actually they are collective. And those collective modes have frequencies that are pretty low. His picture was really, and if I think about this lattice, what if all of them displaced in the same direction? And had some oscillation that looked kind of like the drawing here. So there was some displacement to the right, some midpoint where motion stopped, and then some corresponding restorative displacement to the left. Indeed, he was really the first to think about phonons as these standing waves associated with these so-called acoustic modes. Acoustic just meaning that all of them are going in the same direction. Now, those standing waves have some period, so some lambda. 2 pi over the period spatially is a wave vector. And if it was acoustic, one could measure the corresponding propagation speed with which those standing waves moved. And there would be a so-called dispersion relationship that related that k to a corresponding frequency, in which case for acoustic modes he proposed to be linear. the density of standing waves in a three-dimensional system, if the relationship between k and omega was linear, would imply a density of states of omega. There are, in a three-dimensional box, k squared dk number of ways to point a vector in 3 dimensions, implying that g of omega would go like omega squared. So CV per KB in Debye's model would be an integral over omega relative to some characteristic now known as Debye frequency squared. That's the G of omega term up to some constant factor that's been put into that omega naught. You have the energy gap, beta h bar omega squared, and that Boltzmann factor, like so. If we do a U substitution, say that U is equal to beta h bar omega, or that du is beta h bar d omega, we can rewrite this as being proportional to beta squared, an integral over u, beta h bar minus 1 beta minus 1 u to the 4 and e to the minus u. Grouping terms together, we have a beta squared, beta inverse that kills one of those betas, and then beta inverse to the 4th. That whole thing is going to go like beta inverse cubed times some integral that doesn't depend on temperature, it depends weakly on temperature. Beta to the minus 3 is just another way of saying temperature to the 3rd. And consistent with experimental observations. So in this epic showdown between Einstein and Debye, Debye won out. He had some hindsight of experimental knowledge to inform his model. Not really a fair fight. Okay, so that's a discussion of the harmonic oscillator and where you see them in nature. We've computed their partition functions and now employed them to do a fairly sophisticated calculation, a calculation of the observed heat capacity or the temperature dependence of the heat capacity, noting that at high temperature there's some universal law, the Dulong-Pettit law, that says that it is just some number, essentially that number implied by equipartition. And at low temperature, invoking a model for how many frequencies there are at low frequency, so-called Debye model, we can now predict the temperature dependence of that heat capacity, again, as inherited essentially from a calculation of the partition function. All right, well, that's all I've got for today. Again, I'm holding an extra office hour on Wednesday in preparation for your exam this Thursday. Yeah, so feel free to email me if you have questions. Otherwise, I'll see you then or in the live session later today. Okay.